We've seen a little bit of this linear approximation business already. A long time ago, we saw this, that f of x plus h is approximately f of x. Well, that much, at least, is really just because f is, say, continuous, right? Nearby input should be sent to nearby outputs. But let's suppose that f is differentiable. Then we can say more, right? I'm going to add to this h times the derivative of f at x. What is the derivative measure, right? It's the ratio of how much the output changes to an input change infinitesimally. But for an actual input change of h, if I take this, which is the ratio of output change to input change, and I multiply it by how much the input changes, this quantity should tell me how much I expect the output to change when I go from x to x plus h. Where does this formula actually come from? Well, let's think back to the definition of derivative, right? What's the definition of derivative? The derivative of f at x is the limit as h approaches 0 of f of x plus h minus f of x all over h, right? That's the definition of derivative. Now, how does that help us here? Well, if I just pick some value of h, an actual value of h that's not 0 but close to 0, then I get that f prime of x should be approximately f of x plus h for that small but non-zero value of h minus f of x over h. So this is approximately equal as long as h is small. Now I'll multiply both sides of this approximate equality by h, and I'll find that h times f prime of x should be approximately f of x plus h minus f of x. And then I'll add f of x to both sides, and what I'll get is that h times f prime of x plus f of x should be approximately f of x plus h. And that's the statement that we had before, right? That the value of the function at x plus h is approximately the value of the function at x plus something I'm getting from the derivative of f at x times how much I wiggle the input by. So I've got this formula, but why do I care about this formula at all? Well, I care because this is really what I wanted in the first place, right? I really wanted to understand how wiggling the input would affect the output. And fundamentally, the derivative isn't just some random limit that I've cooked up for you to evaluate. It's supposed to say something meaningful about the function. And this is what's telling us what the derivative means, right? The derivative really means something about how wiggling the input affects the output. There's another reason to care about this formula. We can use this formula, in fact, we've already used this formula to numerically approximate a function that might be hard to compute otherwise. Let's look at a function f of x will be, say, the cube root of x. And let's look at the input 125. And f at 125, right? What's the cube root of 125? That's 5. Because 5 times 5 times 5, that's 125. So the cube root of 125 is 5. Now let's try to wiggle the input and see what happens. Let's wiggle by h, which will be 3. 3 is not all that small, but compared to 125, 3 is pretty small. And I'd like to know what f of a plus h is, right? I want to know what the cube root of 125 plus 3, 128, is. And that's going to be hard to know, right? So I'm only going to know approximately. But I can use the derivative here, right? Because the derivative tells me how wiggling the input affects the output. So I should compute the derivative of this function at the input a. So let's differentiate this function. And this is x to the 1/3. So the derivative is 1/3 times x to the minus 2/3, right? This minus 2/3 is 1/3 minus 1. It's a power rule. Let's compute the derivative at the input 125. So that means I look at 1/3 times 125 to the negative 2/3 power. Well, 125 to the negative 2/3 power, that's 1/25th. And 1/3 times 1/25th, that is 1/75th. So this tells me what the derivative is at 125. Now, how does that help? Well, remember the other formula for this linear approximation game, that f of a plus h, which is what I'm trying to compute, should be approximately f of a plus h times f prime of a. And I know what all of these quantities are now. F of a is 5, h is 3, and f prime at a is 1/75th. And 5 plus 3 times 1/75th, that's 5.04. Now, how close is that to the actual retail value of the cube root of 128? Well, it turns out that the cube root of 128 is actually about 5.039684, and it keeps on going, which is awfully close to 5.04. So our linear approximation game is working really quite well. This idea that a complicated function like the cube root function with its curved graph can be approximated very well, at least for short intervals, by straight lines, right? This idea of replacing curved objects with perfectly straight lines, that's a key idea of calculus. In short, curves are way too complicated for us to understand. Lines, on the other hand, just straight lines, are much easier for us to think about.